Okay, here is an explanation of the derivation of the surface area double integral formula. I highly recommend reading 1066 and 1067 very carefully because I'm leaving out a lot of notational details. I'm just trying to explain the main idea of building the formula. So the goal here is to compute the area of a surface defined by a function fxy over a general region D. We'll start with the rectangular region since it'll be easier to set up the integral in that case. And we're going to go through sort of the usual production of an integral formula, which involves chopping up the object that you're trying to measure into a million pieces and then estimating the quantity on each of those little pieces, and then adding it all back up with the Riemann sum, taking a limit, and producing an integral formula. So let's go ahead and fix a point on the surface. We'll call it xy. And let's imagine if I partition this domain D up into a million pieces, possibly by partitioning the x values and partitioning the y values, then I'm in effect chopping up the surface into a bunch of pieces. So our first goal is going to be to estimate the area of one of these small pieces. The smaller the piece, the more it's going to look like a flat surface rather than a potentially curved surface. So I'm going to construct a flat tangent plane to the surface by looking at some tangent vectors, the first in the direction of the x-axis and the second in the direction of the y-axis. So I've drawn these two tangent vectors. I'm going to call the first one A and the second one B, and then I'm going to think about the components of those vectors. So A is constructed by moving a very small amount along the x-axis, so I'll call that amount delta x, no movement in the y direction, and then what would its z component be? Well, the rise over run to form A in the direction of the x-axis should be the partial derivative of the surface at that point. So the ratio of the z-coordinate to the x-coordinate should be f sub x. So given that, and then similarly for y, these are the components of the vectors that I just drew. Okay, I'm going to use these two tangent vectors to draw a little tangent plane. So I shade in sort of the parallelogram that's formed by the vectors a and b, and that is its own little itty-bitty surface, which estimates the blue piece of the surface pretty well. So now I go back to a previous chapter and remind myself how to compute the area of a parallelogram formed by two vectors. And as you might recall, that ends up being the magnitude of the cross product of those two vectors. So since I have the components of these vectors, I can compute the cross product in the usual way. I'll skip over that computation, but you can do it on your own. And here I'm just dropping the inputs of f sub x and f sub y at a convenience. And this is the cross product vector that I get. So with that cross product vector, I'm going to compute the magnitude of it and understand that that ends up being the area of this little green parallelogram that I'm using to estimate one of the pieces of the surface. So I imagine doing this for many, many, many pieces spanning all the little regions of the domain that I chopped up. And you form a Riemann integral, which in this case varies over x and y, so it's a double integral, double Riemann sum, and its limit will end up being a double integral. So as you can see here, the form of the area of the parallelogram becomes present in the double integral formula. The delta x delta y is the differential unit dA, and then I can integrate over really any region that I like. So that is, I can integrate over a type 1 or type 2 region, or even a polar region, just long as I set the limits of integration up appropriately. The last thing to note here is the similarity between these formulas and the arc length formula from previous chapters.